do problem 45 on page 734. It says, the electrons in a particle beam each have a kinetic energy of K. What are the magnitude and direction of the electric field that will stop these electrons in a distance d? So this is one of those problems you don't have to do any calculator work. It's just all in terms of variables. So let's write down what's given. I've got an electron. Okay, I'll just draw it as like a little e. And it's moving. It's got a velocity like this. And what we want to do is we want to slow it to a stop, which means that I've got to apply a force to it to the left. We've also got some kind of electric field that's going to stop it. And, it's got kinetic energy K. So that's kind of what's given. And then we want to find, and it's going to come to a stop in a distance d. So when it reaches this distance d, the velocity will equal 0 of the electron. Okay? And so what we want to find is the magnitude and direction of the electric field. So we want the electric field. Okay, and so now let's solve it. So now here's my electron. Let me kind of redraw it here. I'll just draw it as a dot and put a little negative e on there. And its velocity is this way, and so I want to slow it down. So I have to apply a force to it in this direction. So this is the force, and we're going to stop it in a distance d. And we have the work energy theorem, which says that the work done by the net force acting on an object, and we'll assume that this is the only force acting here, the work done by the net force causes a change in kinetic energy. So the work done by the net force, well, that's F dot D, and that's going to be equal to K final minus K initial. And K final is 0, and K initial is just K. So we have negative K. And so we know that the force, we already kind of stipulated that the force is in the opposite direction as the displacement. So this is going to be, now the force, what is the electric force on this guy? Well, it's the charge on the electron times the electric field. So it's the charge on the electron times the electric field. Now I'm going to use Q here, but I think the book used E, the lowercase e, for the charge on electron, which is just fine as well. And this is going to be equal to negative K. Oh, but we're saying these are in the negative direction. So this is, you got a cosine of 180 degrees there, right, when you do a dot product. Oh, and I left the D off here. So this is the force times the displacement times the cosine of the angle between the force and displacement, so they're 180. So that gives you a negative 1. So that cancels that out. So the magnitude of the electric field is going to be the kinetic energy divided by the charge on an electron times the distance that it took for it to stop. And so let's do that. That's the magnitude of it. Now, or the book did this. They used the letter E for the charge on an electron, the elementary charge. The smallest charge you can get in normal matter times D. Now, what's the direction of the electric field? Well, the force, you want the force to be to the left, but it's a negative charge. So remember, the direction of the electric field tells you the direction that it would push on a positive test charge. But this charge is negative. So if we want the force to be to the left, the electric field has to be to the right, which is the same as the direction of motion of the electron. So for the direction, okay, we would say it's the same as the moving electron. or the same as the initial velocity of the electrons. So you have to, or if you drew a picture of it, if I saw that the force was this way, and you somehow showed that the velocity, the initial velocity was that way, and that the velocity and the direction of the electric field is in the same direction, I'll give you full credit for it. And I think you actually had that, I think, Anthony, on your paper. So I'll give you that back. So here's the magnitude, and here's the direction of the electric field. Any questions on this? Okay, just one thing. You're going to have problems like this on the AP test where there is no calculator work. It's all about deriving expressions. At first, that can be very aggravating, but believe me, the farther you go in physics and mathematics, the less you'll use your calculator, and actually that's a good thing because calculators just take time to use. All right, and that is all.